So in the last lecture, we had started to look at metathesis reactions in the context of transmetallation. So in this reaction, in this lecture, we're going to talk about some other metathesis reactions. Okay, so the first one we want to talk about is sigma metathesis. So sigma metathesis is the swapping of sigma bonds. So it's a bond switching process where sigma bonds undergo metathesis, or sort of like a switching. Okay, this is a type of transmetallation, it turns out, because we typically use metals or things that are borderline metals, nonmetals. So for example, if we had this titanium with two cyclopentadiene anion ligands, this could undergo a metathesis reaction with a silane. And these types of metathesis reactions always have some sort of driving force behind them because they exist, like anything, I guess, they exist in equilibrium. But here, this reaction is actually driven by the formation of a stable silicon-oxygen bond. And so we could show curly arrows where we just kind of move the oxygen to the silicon, the hydride to the titanium. And so silicon's kind of a non-metal in my book, but it sort of looks like a transmetallation. Anyway, what I want to do now is move into a huge field. Sorry, let me get a new page here. I want to move into a huge field of metathesis called Olefin Metathesis. Sorry, I don't know why that's not working right now. Let's see, let's give this another. Okay, so I'm on that page. Okay, let's just do a few more. So Olefin Metathesis is an interesting word, and it Grubbs and Schrock were awarded Nobel Prizes a few years ago. So for Olefin Metathesis. So Olefin Metathesis, this refers to olefin. It's an interesting choice of words because olefin is a molecule with an alkene. So, but you don't hear people calling this alkene metathesis. You also want to recognize that olefin is not a functional group. So the olefin is not a functional group, but rather it's a molecule. It's a class of molecules with an alkene present. Okay, but again, people don't call these things don't call these types of processes alkene metathesis. So what this is sort of a double bond metathesis or a double bond switching. Okay, so what it looks like is if we consider a pi bonded system, double bonded system where we have A double bonded to B, C double bonded to D, we could undergo a double bond metathesis where then A is double bonded to C and B is double bonded to D. Okay, now it turns out that this was awarded, Grubbs and Schrock, who worked on this, were awarded Nobel Prizes, shared a Nobel Prize for this because they were able to do this in the context of carbon-carbon double bond systems. Really turned out to be quite effective, quite reliable, and as a result, it really impacted the chemical industry in a big way. And so olefin metathesis has all carbon atoms. So what we have here is if we had like C1 bonded to C2 and C3 bonded to C4, all with pi bonds, what we could do is olefin metathesis to get to C1 double bonded to C3 and C2 double bonded to C4. Okay, and I keep saying these names, Grubbs and Schrock. I've heard them both speak while I was a PhD student. I think I even met and presented to Schrock. Based on our interaction, he certainly doesn't remember me. Anyway, that's okay. All right, so ruthenium, for the Grubbs catalyst, we use ruthenium double bonded to to a carbon that's bonded to a phenyl. And PCY3 is a ligand, and PCY3 is a ligand, axial to each other, and then equatorial, we have two chlorine atoms. And Schrock has a molybdenum center instead. And so we have OR with a bunch of fluorines, R with a bunch of fluorines. So these RFs are usually fluorinated alkenes. Okay, so what I have in front of us are the olefin metathesis catalysts. Okay, we have the Grubbs catalyst and the Schrock catalyst. And so what I like to think of these as is a metal, and it's a transition metal, sure, with our molybdenum and our ruthenium. It's a metal that's double bonded to a carbon atom that has an aromatic ring like phenyl versus something else. And so this is just our catalyst to promote olefin metathesis. Now, catalysts are highly powerful, and so you can see why this relates to our unit. I mean, we're talking about metathesis reactions, and we're using transition metals. Okay, so the way I like to think about this as is we have two alkenes that we're going to do a metathesis reaction on. Now, these two alkenes are typically primary in the sense that they've got some R group. I'm going to put a butyl on one and a phenyl on the other. Now, because phenyl is part of the catalyst. I mean, we could use phenyl and have styrene, but let's do it like a cyclohexyl. And so what we can do with our olefin metathesis catalysts which again is TM double bonded to some R group. I tend to draw the Grubbs catalyst more frequently. But what we're going to do is we could make a number of products, but it turns out they would be the same as the starting materials unless we combined this carbon with this carbon. Everything else would just sort of be either a dimer or or it would just be the same starting material. So let's draw this product. What would this look like? This would be Bu. And you know what? I'm going to unhighlight this and change the color of the highlighting. Again, I only grab one carbon of the alkene, but so this would be our product where we've got green bonded with red as a result of the olefin metathesis reaction that is catalyzed, plus some ethylene byproduct. And the ethylene byproduct is from this end on either side kind of coupling together. Now, alternatively, we could have, this is called the olefin cross metathesis product. But you could have a reaction where the green reacts with the green and the red reacts with the red. And certain nuances about what catalyst you choose will impact the likelihood of forming a homodimer or a cross metathesis product. Now, in all of these cases, the byproduct here is ethylene or ethene gas. And if the ethene gas came back in and did a cross metathesis on any one of these things, then we would just see the starting materials be reformed. Okay. So these are some of the outcomes here, and we're going to look at this reaction in more detail for the rest of this lecture, and then we'll sort of call it good in terms of this reaction. But the general mechanism is as follows. There's several sort of, there could be several ligand association events, but I'm just going to talk about in dissociation events. But I'm going to talk about the principal components of the olefin cross metathesis reaction. So what we have here is we have our butane that's attached to an alkene plus a metal that's attached to an alkene with a phenyl group. Now what we're going to do is, I'm just going to continue my highlighting here. This is the green piece. What's going to happen is we're going to do a metallo 2+2 cycloaddition reaction to form a metallo cyclobutane intermediate which will undergo a retro 2+2 reaction to release vinyl benzene, which is styrene. And we have a small amount of styrene because it's from the catalyst, so we don't worry too much about its side reactions. Sure, does it react? Sure, but it's a small amount because we're using this metal as a catalyst. So we've sort of initiated, I guess, you know, in all honesty, the thing that we put into the flask that I call Grubbs catalyst is mostly like Grubbs pre-catalyst, because we're going to do an initial reaction. And it's this product that will turn over subsequently. And based on some sterics and some electronics, you might see this alkene react faster, the other one react faster. And that'll help you control whether or not you get a cross or a homo-coupled product. Okay, so now we have our green piece locked into the metal, and what we can do is the exact same thing, except now we have a different alkene that we could adduct with. We could have our metal, which is double bonded to a butane, react with our, and let's position this way so that we can actually do the reaction with our red piece. So these are going to do a 2+2 reaction, and then a retro 2+2, and I should write retro 2+2 up here. Okay, so we have a 2+2 reaction, and then we're going to do a retro 2+2. And what's cool is we get our metal now bonded to ethene plus our metathesized product. Whoops, I dropped a bond off there. Okay, and this can react with more of this to form more of our metallated species that has this, which makes more product. And so we continue onward through a catalytic cycle, I suppose involving one of these two as the actual catalytic species. Because the styrene that's generated is either rapidly consumed or just kind of goes, it's probably rapidly consumed in a small amount, and it just turns out that with these catalysts you just don't need that much stuff. Okay. So we have our product here. I should add my highlighting to this so we can see. All right. Okay. So now let's do some interesting reactions with this. It turns out that you can do a ring closing metathesis reaction. So you can make rings fairly easily. So what I'm going to do is I'm going to take a nitrogen. This is just an example. I must have gotten this from the book, but it's a pretty cool example. So we've got this kind of crazy system. I mean, it's not super crazy. This looks like isoleucine amino acid coupled with a nitrogen that's got some stuff hanging off it. Okay, so kind of complicated molecule, and what we can do is we can just take this complicated molecule with all its functional groups and its stereocenters and just add the Grubbs catalyst to this. And what we'll do is we're going to stitch together the molecule at these alkene positions. I'm going to have a green and a red, and then I'm going to highlight the yellow ends, which are lost. So we're going to do olefin metathesis here, where we take a molecule that's an olefin and metathesize carbon-carbon double bonds with another molecule. Now this happens within itself, so this is an intramolecular reaction. So this is an intramolecular reaction. Now the outcome of this is, if you count 1, 2, 3, 4, 5, 6, 7, is we're going to form a 7-membered ring and eject ethylene as a product. I've run out of space. So 7-membered rings, everybody's favorite ring structure to draw. I still remember the feedback I got from students when I put a 7-membered ring on an exam that they had to draw. It was like a mechanism problem, so they had to draw it over and over again. Whew, it's not my best work. Okay, so 7-membered ring plus ethylene, and we could apply our highlighting. So red's over here, green's over here, yellow is our ethene product that is formed. Okay, so that's ring closing metathesis. We've closed a ring by taking 2 alkenes that are on the same molecule and doing an intramolecular olefin metathesis reaction. This is sort of how I approach olefin metathesis. I don't worry too much about the curly arrows. I just look for the 2 alkenes that I can stitch together, and I'm trying to make myself able to recognize that I'm going to stitch them together and then, in this case, close the ring. Okay, so we can do ring closing metathesis. We can even do ring opening metathesis. Now, why would you want to do ring opening metathesis? Well, you do ring opening metathesis if you want to, technical term, romp. Okay, that is ring opening metathesis polymerization. Ring opening metathesis polymerization. Okay, so what we're going to do here is we're going to apply the metathesis strategy to open a ring and induce polymerization. Opens a ring, induces polymerization. Now, this is a really cool polymerization strategy because it actually is highly effective as far as polymerization goes, and it enables itself to work with a range of molecules and a range of functional groups. Okay, so what this looks like is we're going to take a ring. Let's just take a cyclopentene ring. And what I want to do is react this with, let's pick on Grubbs catalyst again. So my metal is going to be ruthenium, and then we have this kind of styrenyl side chain. Now what we're going to do is our 2+2 reaction, which is going to give us a metallocyclobutane, 4-membered ring with a metal present. I'm going to have this phenyl hanging off here. So I did the 2+2 reaction. Now I'm going to do a retro 2+2. This works. Okay. So I'm going to do a retro 2+2 to form this species. Now, if you look at this, we've done a ring opening reaction. All I'm going to do is just twist this molecule around this way. So I'm just going to twist the left and the right sides around so that we can see the polymerization event. But if you notice, the ruthenium is now built into the molecule, that we've not only cracked open the ring, but we've not only cracked open the ring, but we have incorporated the ruthenium into our molecule. So what we can do is add another cyclopentene. I mean, and it's just floating around. We could do another 2 + 2 cycloaddition to make another, let's see, phenyl. That alkene's still there. Ruthenium. Okay, then we can do another retro 2 + 2 reaction going this way. So we've not only ring opened this second ring, but we've incorporated we've taken our double bond from our first ring and put it into the double bond of the second ring. And the product looks like this. And that's probably E I should add at this position. 1, 2, 3, 4, 5. The structures get kind of gnarly. But anyway, this can kind of keep going to make interesting polymers. And cyclopentene was just one example. So again, this is called ROMP, is the term everybody uses. Ring opening metathesis polymerization. I'm sorry for the crude joke. Didn't mean it. But we get to an interesting polymer, and if we want to take our structure and draw a repeat unit, 1, 2, 3, 1, 2, 3, 4, 5 atoms, N. So that's our repeat unit. We actually get everything from the alkene chain. And so you can really build in some interesting side groups, and those interesting side groups invoke interesting properties in the overall polymer structure. Okay, so I'll do it for olefin metathesis, and we're going to continue to discuss more interesting reactions in the next lecture involving transition metals. Okay, so until then, I will see you next time.